Good day to all. I'm Dr. Suresh Venkatesan. What I want to talk to you about is our developments in a photonic interposer that can extend wafer-level chip-scale packaging to the world of photonics and photonics electronics co-integration. The outline of my talk, I will spend a bit of time introducing and motivating the concept, as well as providing application proof points on the photonic interposer, and then finally conclude my presentation. So photonics is undergoing a revolution today in much the same way as electronics underwent a revolution these past 3 decades. And silicon-based integration platforms are really a key to this predicted explosion in growth. Photonics has historically had its presence felt in data centers for optical connectivity, but increasingly, there are new applications of photonics, primarily in alternate compute technologies, high-performance compute, chip-to-chip communications, AI, ML, inferencing, and machine learning, and then automobiles with regards to the next generation of FMCW LiDAR technology. And then, of course, there's the proliferation of photonics in wearables for target detection, healthcare, and for sensing applications. These new applications of photonics far outweigh the volumes that have traditionally been driven by data communications and data centers, and then hence new ways of putting photonics devices together, combining in photonics and electronics becomes critically important. So what are the key challenges in photonics? The issue primarily comes down to packaging and known good die, right? And current technologies, especially discrete micro-optics-based packaging technologies, are simply not scalable for the applications that require hundreds of millions and billions of units a year, right? So you can make do at 100, 200, or 400 gigabits per second, putting out, tens of millions of units a year, conventional micro-optics based assembly. Of course, there's an installed base. People have been doing it for 25, 30 years. But at some point, you reach a point of diminishing returns, both in terms of cost, scalability, your ability to supply the volumes necessary, and of course, performance as well. And on these merits, so in volume, size, cost, power consumption, performance, we believe that a photonics interposer technology, like the ones developed by POET, become far more attractive. And the reasons are, with a photonics interposer, you're talking about manufacturing hybrid components, which means known good die, best of breed technology and components. You're talking about wafer level test, wafer level packaging, which people do in the world of semiconductors today. The components are integrated into a virtual single chip, hence the term chip scale packaging, and wafer level chip scale packaging, which is of course being used in electronics today, doesn't exist in the world of photonics. And we believe a photonics interposer technology does enable wafer level chip scale packaging for electronics photonics co-integration. And everything is fully integrated electrically and optically, eliminating wire bonds, and enabling proximity of placement, which all results in improved performance, especially for high frequency RF, as well as improved power consumption. So these are what we believe at POET to be the fundamental benefits of adopting a photonic interposer technology concept for next generation photonics applications. So what is POET's solution, which is the photonics interposer? We believe we've developed what we call the POET Optical Interposer, which is the first ever chip scale hybrid integration capability in the world of electronics photonics co-integration, where hybrid photonics components can be integrated into a virtual single chip using wafer level processing, assembly, and test. What we did was extend the concept of a traditional electrical interposer, which is used today, right? RF interposers are used all the time in high performance compute specifically, combining GPUs with memory, GPUs next to CPUs. And really the intent is, put electrical die in close proximity to each other and use an RF capable interposer that can combine the signals between these two die. And especially these days in semiconductors, people are talking about chiplets. And you will see me talking about chiplets later in this presentation in the optical domain. But nevertheless, the moment you disaggregate systems into chiplets, the interposer becomes a very critical bridge that marries these components together in terms of performance. So what we did was took the fundamental concept of an electrical interposer and added optical functionality to it, right? So rather than doing just simply electrical interconnections between die, we now enable optical interconnections between die, and that's what we call the POET optical interposer. This optical material or waveguide system that we include in part of the interposer is done in a standard CMOS fab, can be done at 8-inch or at 12-inch. And basically, the resulting photonics interposer, or the optical interposer, is a sandwiched stack where you've got layers of optical waveguides sandwiched in between layers of electrical waveguides, which gives a very unique structure to this photonics interposer and enables some unique capability that you will see later in my presentation. That optical interposer is then converted into an optical engine through hybrid integration. And this largely entails flip chip processing of either electrical components or optical components or both, right, on an optical interposer. So that the end system or subsystem that you get after the assembly of these components is what we call an optical engine. And so this concept that we've invented with the photonics interposer, has three primary vectors that drive its performance and drive its applicability and ubiquitous nature of the solution in terms of the various markets or the various verticals or applications you can use it. The three vectors are basically chip scale. So the components are integrated like a chip scale package, right? And they can be over molded too, which makes for some really interesting applications downstream. We use hybrid components. So these are known good, best of breed components. And we think that's important because rather than being married to, okay, I got to use a ring resonator and silicon photonics built a certain way. I mean, you have the flexibility of all the new materials that are coming downstream, whether it be BTO or lithium niobate. And an interposer allows hybrid components to be used more effectively. And the third primary vector, it's that all processing is done at wafer scale. So, rather than building modules one at a time using active alignment and, micro optics and so on, we use, conventional semiconductor flip chip processing technology and carry out the assembly processes at wafer scale. So that in principle is what our, interposer solution is. What it looks like is effectively it's a passive solution, right? So we include electrical passives and optical passives in the interposer, and the active functionality is achieved through hybrid integration. And you will see on the slide at the bottom left that it shows you how we architect this sandwich stack where we can have up to 2 layers of non-interacting optical waveguides sandwiched in between layers of electrical waveguides, and the electrical waveguides communicate, signals electrically between die, and the optical waveguides communicate the optical signals. We do have, the way we architect our system is we include, the ability to get light in and out both vertically as well as horizontally. So in our applications, we get light into the interposer on the horizontal plane with lasers. We get light out of the interposers in the vertical axes, directly coupling into photodetectors. We can include through silicon vias, just like you would with any standard, interposer technology that allows you to get very tight placement and close proximity in component integration. And one of the areas that we've really spent a lot of time working through is architecting the thermal aspects of such a photonics interposer. And we've built some integrated heat spreaders into the interposer that allow us to take heat out of the lasers effectively. And that is a very critical requirement. So, compared to standard electrical interposers, a photonics or an optical interposer needs to address, 4 primary parameters. One is mechanical integrity. You're flip chipping these components. They need to have a certain shear strength and mechanical stability while they're on the interposer. Second, they need to have very good electrical contacts, of course, and the electrical characteristics of the interposer should be good with, especially for high frequency RF applications. Third, you have to have great optics. I mean, nobody's going to use this if the optical capability of that interposer is very good. So you need best in class in terms of optical performance. And last feature that not too many people talk about is thermals. We do assemble lasers that are relatively high power on these interposers, and your ability to be able to take the thermal heat out of the lasers out, and your ability to have some thermal isolation such that lasers are not heating up the electronics next to it and vice versa become a critically important part of architecting this photonics interposer. And we've spent several years architecting this, and we're happy to show that we can deliver what we believe is the world's smallest single chip package or a chip scale package for an optical engine that is for 100 to 400 gigabits per second application. And you can see here that, in a simple 6x9 millimeter footprint, we're able to incorporate, all of the optical passive capability with the muxes, the demuxes. We've got, hybrid lasers attached down here, thermistors, photodetectors, monitor photodetectors. So the entire subassembly that is traditionally using ROSAs and TOSAs and so on and so forth is really brought together in a really tiny form factor. In fact, this form factor is so small that you can actually fit about 4 of these inside of a QSFP-DD. And we do have customers taking advantage of that form factor and creating some unique custom solutions when it comes to data and telecom modules. One of the challenges in data communications really it comes down to spatial division multiplexing and its growth, right? So at 10G, 40G, up to 400G, the channel counts went from 1 to 4 with WDM. But beyond 400G, we're talking about 8 channels going to 16 channels at 1.6 terabits at 100 gigabits per lambda. And then, of course, down to 8 again as you get to 200 gig per lambda, but then increasing beyond that again. So we're really talking about needing to integrate 8 to 16 channels, right? And conventional means of integration just simply do not work. And the more functionality and the more number of channels you try to cram into the form factor of these modules, the more important these photonics interposers become, and the more applicability the POET optical interposer has in these applications. On the top is an example of a conventional discrete assembly. This is an 800 gigabit per second FR4 module. And it can be done. It's not that people can't do it. It's just cumbersome. It uses a lot of individual pieces, multiple active alignments. And we believe that for scaling, especially in volume, these are unsustainable for 8 channels. And it becomes practically impossible for 16 channels, right? You try to do a 1.6 terabit per second using conventional optics in an OSFP-XD, it's going to be really tough. And the POET solution is about 75% smaller in size, right? So below, we show what an interposer-based solution using our technology looks like. In this case, we've architected our engines as chiplets. So we do 2 400 gigabit per second chiplets that are placed right next to each other on the board with 1 800 gigabits per second receiver. And that's it. The rest of the board is completely unutilized, right? And that's what the power of the integration is. That's what the power of such an interposer technology can be. And in this solution, of course, there are no wire bonds. The TIAs, the drivers are attached on the interposer right next to the components. There are through silicon vias in the interposer that attach it to the PCB, and it's a super clean solution as it relates to placement as well as signal integrity. So the example of the kind of design flexibility offered, so this is just an example of our 400 gigabit chiplet that we're building now for 1.6 terabit applications. It's 3.7 millimeters on a side, so you can put 4 of them right next to each other and still fit comfortably inside of an OSFP form factor. We use flip chip drivers and lasers for low latency. All pads are reconfigured on the interposer to exist only on a single facet so that these interposers can actually be concatenated edge on edge. Through silicon vias for signal integrity and ground, we have integrated athermal low loss multiplexers, demultiplexers for the receivers, integrated power monitoring, and integrated passive devices, right? MEM capacitors, resistors. So there's a certain degree of bypass capability on the interposer itself that allows for these components to kind of coexist. And you can see that such a highly integrated functionality from an interposer perspective then lends itself to a very simple implementation of a 1.6 terabit architecture on a board where you concatenate 4 chiplets. And it really, these are known good die chiplets, right? So you assemble individual chiplets and then you assemble them on the board, again, with through silicon vias and no wire bonds. So this just gives you a sense of what a photonics interposer or POET's optical interposer in this particular example can do to kind of, these really high channel count data center applications. Why scale and signal integrity matter? And I'm not professing to say that we can in fact eliminate the DSP, but especially with these with the new Tomahawks, the DSPs are no longer doing the gearboxing, right? So it's primarily there to clean up the signal. Now, what we can do, at least from a module perspective, is due to the form and size and scale and form factor associated with these engines, you can move these engines all the way to the butt of the receptacle, right? So you completely eliminate the traces at the module level. So we can take care of, the module in terms of being capable of, quote unquote, eliminating the DSP, provided, of course, the host board has the right signals and the clean signals coming in. There is that possibility. Now, while we can't say for certain that this can work in terms of direct drive, we do believe that this is the best shot the module has, right, from a pluggable perspective, to be able to eliminate the DSP and get into direct drive. And that has huge implications, right? 6 to 8 watts of power reduction per module, which is huge. And it enables the kind of performance people are talking about getting from a co-packaged optics, but in a much simpler and more versatile pluggable solution and a pluggable form factor. So our interposer's key competitive differentiators, by virtue of the fact that we are in fact a hybrid solution, we do have the ability to, within the context of an interposer, provide a complete solution, right? Starting with flip chip modulators or modulated lasers, multiplexers, demultiplexers, the electronics, as well as the receive. If you compare it to kind of, more, pure silicon photonics as it is being implemented today at 100 and 400, most of those solutions have struggled on the receive side, and in many cases have also struggled in terms of, providing appropriate WDM functionality. So, most of the success has been in parallel optics, moderate success in WDM. But even in the WDM architectures, they have struggled on the receiver side where, more conventional micro-optic solutions have been used. And so it hasn't had really the kind of impact. And so EML-based solutions still own 80 to 90% of the market, right? And so we believe that, an interposer solution, which is hybrid in nature, that is equally applicable to silicon photonics components as it is to indium phosphide components, we believe can be unifying, and we believe provides a far more complete solution for next generation data centers. So our application platforms, are for directly modulated lasers, 100 through 800 gigabits per second. We also have a CW platform that we use to provide, remote light sources for, multiple applications, including AI, ML, et cetera. So in terms of light sources for high bandwidth communications, we have the ability, of course, to, assemble passively at wafer scale various lasers, and have the ability as well to provide some degree of splitting, multiplexing as the application requires. And this eliminates the need to use laser arrays, which are quite expensive. It meets the cost, form, scale requirements for really the high volume applications, and also provides very good laser coupling efficiency. And really the other major advantage of these optical interposers comes in integrating new materials. If you think about thin film lithium niobate, for example, a great technology has the ability to go to 200 gigabits per lambda readily, but it lacks integration capability. So, an interposer allows that lithium niobate modulator to coexist with the other components like the MUX, the DMUX, the CW lasers that are needed in a highly integrated form factor that then allows it to be utilized in these next generation solutions at, very high channel counts. So that is another major advantage of, using an interposer technology versus trying to do everything monolithically, because it gives you that flexibility with regards to new material usage. So in terms of application proof points, very quickly, flip chip lasers on our engines are passively placed with no lenses, and they perform exceedingly well from a thermal perspective. These are data taken out of DML lasers. These lasers are tiny; they're the smallest lasers, sometimes even smaller than VCSELs. And we're the only company to truly flip chip bond at volume DML lasers on an interposer platform and demonstrate good optics as well as good thermal characteristics. The filters, of course, as I had said, need to be very high performance, and we're happy that our filters on our material systems are truly best in class. These are passive filters, with less than 2 dB insertion loss. That includes the fiber coupling, right? Which is, I believe, best in class, with greater than 25 dB crosstalk margin. And these designs have been qualified now, and we're proliferating them on all of our 100 gig, 200 gig, 400 gig, and beyond optical engines, both for the receiver as well as for the multiplexer on the transmit side. We provide industry-leading fiber coupling performance. Our fiber coupling is less than 0.5 dB per facet on, by and large, which is best in class. For most part, we see numbers that are closer to 0.3 to 0.4 dB per facet. We do use vertical coupling mirrors to couple light vertically upwards into photodetectors, and we use them either as linear mirrors or paraboloid mirrors, depending on the application. For our 400 gig and 800 gig applications, we use a paraboloid shape on the mirror so that it focuses the light into the photodetector and provides for better performance. The mirror performance itself is good. These are built in a CMOS fab, right? So the yield of these mirrors, you can see, greater than 95% by and large, and very uniform performance across wafers, as you can see on the right, both before bonding the photodetector as well as after bonding the photodetector. We maintain the flat top response of the demultiplexers, and we maintain the good crosstalk and good crosstalk margins that we had seen before. We have, of course, applied this to 100 gig optical engines, demonstrated great eye performance, 200 gig FR4. So this is a PAM4 implementation using the optics and the photonic interposer. We've also done LR4, which is the industry's first chip-on-board implementation for an LR4 system for 100 gig, and demonstrated good both transmit as well as receive. We've, of course, also implemented this for 400 and 800 gig receivers, which are now going through qualification. And really, at the CIOE this year, we were going to demonstrate a 1.6 terabit receiver. So we've been able to really scale this up to a 16-channel implementation of a photodetector in a form factor that fits inside of an OSFP with excellent performance across all 16 channels, right? And this is receiver sensitivity with at least 3 to 4 dB of margin as tested on our evaluation boards. So in conclusion, a photonics interposer like the POET optical interposer that we have developed enables a very flexible architecture for multiple applications that require photonics or photonics electronics co-integration. These can be applied either to modulated lasers like DMLs or EMLs, to CW lasers, and also to create remote light source solutions for for other silicon photonics applications that require remote light sources. We believe it's a very, very compelling architecture for the future that should be considered when architecting next generation photonics systems or subsystems. Thank you for your time, and I appreciate your attention over these past 25 minutes or so. Thank you.